We'll do some kind of find points and random topics in linear regression to wrap up. One is multi-collinearity, which is a long word for just when variables are correlated with each other and what issues that may cause or not cause. Flexible regression, so basically squiggly lines instead of straight lines, how to do that within the same framework using polynomials and splines. The problem of overfitting, and regularization as a way to deal with the problem of overfitting. So the first thing we'll learn about is multi-collinearity. When covariates are very strongly associated with each other, then their coefficients in a regression model are going to have very large standard errors. The intuition about this is that, let's say x1 and x2 are very strongly correlated, then it's very rare for x1 to vary, but x2 not to vary because they vary together. So there's actually not a lot of information in the data about what happens when x2 varies and x2 remains constant, and vice versa. So the coefficients for both x1 and x2 wind up having very large standard errors. And this is appropriate because there really isn't a lot of information in the data to tease apart the relative kind of effects, not causal effects, but effects of associations between x1 and the outcome and x2 and the outcome. Okay, so let's just do an illustration to make this clearer. Let's just do the full screen. Okay, so first, let's just see what happens when there's no multi-collinearity, when the coefficients or when the covariates are not associated. So we just have x1 and x2 both being independent normal variables. And here's what they look like plotted against each other. It's just a ball, right? They're not associated with each other at all. And then we'll generate y from a regression model, basically with coefficients 1 for x1 and 1 for x2. And then we can fit a model for regressing y on x1 and x2. It's the correct model. We can look at the summary, and we get very close to the true coefficients, right? They're both close to 1 and very low standard errors. Everything works as expected when x1 and x2 are not associated with each other. And if you predict for the value x1 equals 1 and x2 equals 1, what the value for y will be, it says it's going to be close to 2, which is correct, and it's pretty certain that it'll be close to 2, right? So good predictions. All right, so now let's have highly correlated x1 and x2. So x1 is going to be a standard normal variable. x2 is going to be a normal variable with mean of x1 and standard deviation 0.01. So it's going to be very close to x1. And here's what that plot looks like now of x1 versus x2. They're super strongly correlated with each other. So they're highly collinear. So now we can again y from the same regression model as before as a function of x1 and x2. And we can fit a regression model for y given x1 and x2, just like before. So instead of 1 and 1 with standard errors of 0.03, it says one is -4, the other is 6, and there are these standard errors of around 3. So it totally breaks. It's very uncertain about both of the coefficients. But let's do a prediction for the value when x1 equals 1 and x2 equals 1. It's exactly the same as before. It says it's going to be 2, and it's pretty certain about it. So when you have collinearity, it has no idea what the coefficients of x1 and x2 are, but it still knows what the expected value of y given x1 and x2 is. However, note that if you try to make a prediction for values of x1 and x2 that are not seen together in the data, so here with x1 equals 0 and x2 equals 1, scatter plot, that's totally empty, right? Up here. What? Oh, wait, hold on. Sorry. I did predict mod instead of predict mod 2. Here, sorry, it's the same message holds. Sorry, before I did the exact same, I did the prediction from the first model. That's what I was showing you. The prediction from the second model for x1 equals 1 and x2 equals 1, it is similar to the first model. In fact, it's better. Like 2 is correct, right? And it's pretty certain. Same message, just slightly different numbers when I put in the correct model. But now when I try to predict what will happen when x1 equals 0 and x2 equals 1 with the new model in this area where there's no data, it says 5.8 when really it should be 1, right? Look at the confidence interval, negative 0.5 to 12. So when should you care about this? In classic statistics books, they spill a lot of ink over this. There's rarely reason to care about it. In causal inference, for example, if the confounders are collinear, their covariates will have big standard errors, but you don't care because you don't care about their coefficients. We talked about the table 2 fallacy, which is basically to care about coefficients of things that aren't the treatment in a causal inference problem. So it doesn't matter, right? We just care about the predictions. And in standardization, we only ever predict using covariate values that actually literally appear in the data. It doesn't hurt us. We're not needing to extrapolate. So we basically just don't care about it in causal inference. In prediction, if you're not extrapolating, then multicollinearity does not cause problems. It doesn't lead to bad predictions. And you should always not extrapolate too much, right? Whether your data are multicollinear or not, you should avoid making predictions that are outside the range supported by your data. And at least if your data are collinear and you're making a prediction that's outside the range, it'll be flagged by the giant standard error. But the reason it's still good to be aware of collinearity is because it has always been discussed a lot in statistics textbooks. There's someone might want you to worry about it, like you might be doing a causal inference problem and someone might hassle you about your confounders being collinear. It's good to know that it's not really a problem and you can tell them that. And also sometimes model estimates will look weird because of collinearity, like as we saw. The next topic is flexible regression. Sometimes the relationship between the outcome and a covariate is not linear in the covariate. For example, I simulated this data so that the conditional expectation of the outcome given the covariate follows this formula, 3 times x plus 2 times x squared, which is not linear in x. And if you fit a linear regression to it anyway, assuming that it is linear in x, then the fit won't be good. So we've also talked about how you can do a multiple linear regression where you create like another predictor, x squared. So you have 2 predictors, x and x squared, and fit the regression of y on x given those 2 predictors. That's the green line here, and that fits well. And the way to do that in R is to do outcome y squiggly x plus I of x squared. If you want to create a new predictor, that's like a function of another predictor that's in your data, you put it in I of x squared. That creates an x squared predictor. You don't have to stop at just squares. You could do very high order polynomials. Like you could specify this regression a plus b1x plus b2x squared plus b3x cubed plus b4x to the 4th. And you just have I of x squared, I of x cubed, I of x to the 4th. And that's going to be even more flexible as a special case where b3 equals b4 equals 0 here. So these guys go away. It's actually the exact correct model, right? So it's not misspecified. It's more flexible than required, but it's not misspecified. The more flexible you get, the more capacity you have to fit more complicated relationships, and you're not actually misspecifying the model. Like you can still match pretty closely. Something to be aware of though is again extrapolation. The data here were between -2 and 2. That's where all the actual data lie. Here we're doing from -4 to 4. The green line is the second order polynomial, which was like the true model that the data was generated under. The blue line is that 4th order one, which matched the green one pretty closely in the range of the data, but then just goes crazy when you leave the range of the data. So basically, highly flexible polynomial regressions can be nice. They can match basically any relationship, arbitrarily curvy, but just beware of extrapolation with them. They're like especially crazy and bad when you extrapolate. So another option for squiggly relationships is to use splines. instead of adding like x squared, x cubed, x to the fourth as your extra predictors, splines use a different special set of functions of x. They're called basis functions that have some nice properties, and we won't go into the details of how these basis functions are created or chosen. Just know that you can also use spline basis functions to produce squiggly flexible regressions. And here's how to do it. It's very simple. So here I'm just reading in the NHAFS data set again. And I'm plotting average diastolic blood pressure against age. So this is the average for people who are 30, 31, 32, 33. You can see it's curvy. We could fit a simple linear model to it, just TBP as a function of age. And that's what the line would look like, and it wouldn't be a great fit. We could see that it's not a good fit by looking at the residual plot. I guess you have to squint to see this, but you can see the pattern of it going up and down, right? You do have to squint to see this, but you could. And then you could say, okay, I want something more flexible. You could use the package called splines. So that's a package that you have to install. And in particular, there's this function BS, which makes the spline basis for a variable that you're interested in fitting a flexible relationship of. So here we can create, purely for illustrative purposes, just create the spline expansion of age. Instead of 30, 31, 32, it has these weird numbers. They're not really interpretable, but they're what you'll use as predictors instead of the actual age. And the way to use them as predictors in a linear model is just to say, instead of diastolic blood pressure, instead of regressing it on just age, you regress it on BS of age. So it's using the spline basis. And there you go. And now you can predict new values from that model. It's multiple functions of x. They're called basis functions, and they're complicated functions that are designed to result in nice, smooth functions when you use them as regression covariates instead of the original x. So in the same way that if you add x squared and x cubed and x to the fourth to x and put those as covariates in a regression model, you get like a squiggly line. The same happens with these spline bases, and they have nice properties in terms of how well they capture flexible relationships. I think they're preferable to polynomial regression. When I want to adjust for a continuous covariate in a model, I would typically do this. I would do BS age. Remember in the NHEFs, for all the continuous variables, they added square terms, and that was for simplicity, but I know that the author of the book does splines of the continuous covariates. I would never think about it too much. I would just do splines. Like when you think that you need to capture a squiggly relationship, then you should add it. Let's say it's a confounder and you think it's related to the outcome in a squiggly way, then you would either add some extra polynomial terms to your regression, like squares, or splines. I just typically use splines, but I don't know that there's really like a great argument for one or the other. Just another good arrow to have in your quiver for when relationships are not linear in the covariates, but you can still accurately model them. I showed you the example that I worked on where I was looking at the effects of this ventilator setting called PEEP on a measure of how hard the patient is working to breathe called driving pressure. And I used both actually. I used square terms for some covariates, and then I also used spline expansion of hours after ICU admission. It can also improve predictions if relationships are nonlinear. So you'll just get better predictions if you're more flexible. That brings us to overfitting. So all this talk about how good it is to be flexible, you can be too flexible, right? We're talking about how great it is that you can fit as flexible a model as possible and be almost sure that it's not misspecified because it could capture practically any relationship. Here's the problem with that approach. An illustration of that problem is that in theory, it would be possible to actually fit the data exactly. So you could make the regression line go through each point if you include enough predictors. So here I just generated 8 points from this very simple regression where the expected value of y given x was 4 times x. And then I fit this linear model to it with a 7-degree polynomial. And here's the fitted regression line. It hits every single point, kind of like a skier who has to go through all those flags in a downhill race. Before we get to why it's bad, when does this happen? So if the number of predictors approaches the number of observations, and it doesn't have to just be like polynomial or spline regressions or other examples of where you make a bunch of transformations of the same variable. It could be you have age, you have sex, you have race, you have a million covariates, and you don't have that many observations of the outcome. This can still happen. You can still make it so that you perfectly predict as a function of the covariates that you have every single outcome point. Now, something to note is that it doesn't cause bias, where bias technically means here that over millions of samples of the data from the same population, the average of prediction from an overfit model will approach the truth. So if you do it a million times and you take the average, let's just look at this example here. A million times you get crazy squiggles. You take a new 8 points, get crazy squiggles, get a new 8 points, more crazy squiggles. The average at any given point of the million squiggles that you got will approach the true line of 4 times x. So they're not biased in that sense. They're not misspecified either. They include as a special case the truth. However, why is it bad? I think it's intuitive that it is bad, but let's lay out why it's actually bad, because maybe it's hard to think about if it's not misspecified and it's not biased, why is it actually bad, even though it seems clear that it is just from looking at it. So there's a bias-variance trade-off. So the bigger your model, like the more predictors you have, the less biased it will be. So that means for some coefficient values in that model, it will come close to the truth. So again, in this example, for the coefficient values 4 for just the x term and then 0 for everything else, that would be the truth of how these data were generated, right? If you have a super flexible model with tons of predictors for some coefficient values, it contains the truth in it somewhere. That's what not biased means, basically. But the bigger your model, the higher the variance of its parameter estimates and the higher the variance of the predictions it will make for the outcome. And also, the less likely it is that the estimates and predictions from a particular sample will generalize to other samples. No matter what your sample is, it will be sure to exactly fit it. And you know that conditioning on some random 8 points, you know that the squiggly line between them is not going to generalize to another 8 points. So that's why it's bad. And it's also high variance. Like for each set of 8 points, you're going to get a very different squiggle. So there's a bias variance trade-off here. You reduce the bias in that you're sure that you contain the truth, the true model somewhere in the space of models you might estimate. But there's also a lot more variance in your predictions. And it's called overfitting because it matches the particular sample too well at the expense of not generalizing to other samples. What to do about it? The simplest solution that you should probably use most of the time is just don't include too many predictors in the first place. And a rule of thumb that people use is have at least 10 observations for each term in your regression model. That includes interactions, power terms, etc., spline expansions, all that stuff. When you do summary of a model and in R, all the coefficients basically of the model, that's the number of terms in your model. That times 10 should be less than the number of observations in your data set. So with tons of data, you can fit really flexible models and include a lot of predictors and adjust for a lot of stuff. But with interactions and flexible transformations, that adds up very quickly to a lot of terms. And also many data sets have thousands of variables. You usually have to do some kind of restraining yourself from fitting as flexible model as you would like to keep to this 10 observations per term rule of thumb. One way to detect overfitting is have a holdout data set. Say, I'm going to fit my model on this chunk of data, and then I'm going to see how well it predicts on this chunk that I didn't fit it to. And overfit models will fit perfectly the data that they were fit to, but predict very poorly outside of the sample that they were fit to. And cross-validation is a way to assess how poorly. So it splits your data into a bunch of chunks. So for example, 10. and it would fit the model to 9/10 and hold out 1/10 for evaluation. And you see how accurate it is for that remaining 1/10. And then you take turns with the data chunks, letting them be the one that you hold out while you fit the model to the other 9/10. And then you take the average of how well it does on each of those 1/10 chunks when it's its turn to be the holdout. And if it does much worse on those 1/10 chunks than on those 9/10 chunks, then there's overfitting. And there are packages to do this procedure, cross-validation. You don't need to worry about coding this. Just know that it exists as an approach to detect this problem. Another issue that can arise is, what if you don't know how to choose your variables? So let's say your data set has thousands of variables and the code book is just overwhelming, and it would be way too much effort basically to try to understand what the right variables to include in your model are, and you want some kind of automated way to select what variables to include in your model. There's this approach called penalized regression or regularization, which modifies standard regression. So standard regression minimizes the sum of the squared residuals, the sum of the squared errors of the observed y's minus the predicted y's, which is a plus bxi, right? So it finds the a and b such that when you predict everyone's outcome using a and b, and you see how far off you were and square it, you get as low a sum of those squared errors as possible, right? So that's trying to fit the data as well as it can. A penalized regression says minimize that plus a penalty for how large your coefficients are, how many of them are far from zero. So it's saying you have a bunch of coefficients b, like b1, b2, b3, right? And it's saying minimize, find the b's that do as well as possible at predicting the y's, subject to the sum of the absolute value of the coefficients not being too high, like times some penalty factor. And alternatively, you could do the sum of the squares of the coefficients not being too high. So it's saying do more with less. Fit the data as well as you can, but without assigning coefficients that are too far from zero to too many covariates. You know, the bigger the coefficients are, here are the coefficients from that crazy model that I fit to the 8 points, and you can see how crazy they are. So the bigger the coefficients are, the more you would get penalized by these penalty terms, like the sum of the squares of these coefficients is enormous. So you wouldn't choose to fit the model in this way because sure, you get this part to be zero because you exactly match all the y's, all the residuals are zero. But this penalty part is huge. So if you're trying to minimize the sum of them, you're not going to choose these super high ones that lead you to exactly match the data. You'll choose covariates that give you a reasonable fit, make this small, but then also don't make your penalty blow up. So here's a demonstration of this concept. That tuning parameter, lambda, that controls how much you penalize the coefficients for being too far from zero. So if lambda is 0, you're not actually penalizing at all. And if lambda is really big, then there's a big penalty. The bigger lambda is, the more you avoid overfitting. In this demo, this thing lets you make lambda bigger or smaller. And this orange line is your prediction for y for each value of x using a degree 5 polynomial. So when you make lambda huge, you're saying any deviation from 0 of the coefficients is going to be severely punished. So it makes all the coefficients 0, and that leads you to predict that it's always going to be 0. And if you don't regularize at all, then it's just going to do its overfitting thing. And then if you do degree 12, if you don't regularize, it'll overfit. But now let's regularize again with degree 12. And you can see like the more you penalize it for giving big coefficients to those higher order terms, the more like reasonable it becomes, right? The less squiggly, the smoother it becomes. So that's how regularization works. Depending on which penalty you use, like between lasso and ridge, the behavior is actually different. You're not excluding any variables from the model. However, if you use the lasso penalty, which penalizes the sum of the absolute values of the coefficients, it tends to set up a lot of the coefficients to exactly 0, which is essentially the same thing as removing the covariate from the model if you say the coefficient is 0. So effectively you are if you use lasso. Whereas with Ridge, it shrinks all the coefficient estimates towards 0, but it doesn't make any of them exactly 0. So they behave differently in that regard. Are increasing bias, there's a bias variance trade-off. So they're both biased. Whereas OLS, or ordinary least squares, the regular version that's not penalized, is not biased. But we saw before that those overfit models, which are not biased, are very high variance, and it's not a trade-off you want to make. Like, they're too high variance. So by using regularization, in some instances, you trade off a little bit of bias for a huge reduction in variance, and it's like worth it. Another natural question is, if you're using these things, you saw how when I was toggling that tuning parameter in the demo, it changed the behavior a lot. So how do you know what tuning parameter to use? You can use cross-validation for a bunch of possible choices of the tuning parameter. You can see which leads to the best out of sample prediction. So the best predictions on data points that were not used to actually fit the model. And whatever lambda leads to the best out of sample predictions, that's the one you would choose. A drawback of this approach is that standard errors are not straightforward. When you choose a tuning parameter using cross-validation, it's called like a data adaptive estimator. It means like you use cross-validation to decide what's the best tuning parameter. It makes it not straightforward to compute standard errors for the coefficients or the predictions, and Bootstrap doesn't technically work anymore either. So often this is more used for prediction when really what you care about is just making the best possible predictions and not so much quantifying uncertainty.